All right, in the Unit Circle Day 2 lesson, we're going to continue talking about what we were doing last time. This time is going to be a little bit longer, but the good news is there's very little work to do at the end. But there's a lot of super important concepts that you're going to have to really learn about, and there isn't a ton of homework about it. It's more about, watching this video, getting the concepts down. You might have to watch it a couple times, or in the future watch it again to help yourself really get a handle on this. Those of you are going to continue in a higher level mathematics. All right, so before we start, let's remind ourselves about pi. Everyone knows pi. It's that special magical number, right? Pi is what we call a mathematical constant, which means it's a fixed value and there's a clear definition for this value. So pi is defined by the circumference of a circle divided by the diameter. So what does that mean? So think about any circle, right? If you take the circumference of it, and this is how pi was discovered, right? If I take the distance around the outside, which is the circumference, right? And then I also measure the diameter. We could also do this with the radius, but we'll just focus on the diameter for now, right? Well, if I take those two and divide them for any circle, no matter what, if I take the circumference and divide it by the diameter, for any circle, no matter what, I always get this number pi. So that's why we call pi a fixed value, and that's its clear definition, right? And that's how we came up with the formula for circumference of a circle. Obviously, you can multiply both sides by diameter here and find the diameter or circumference of any circle by going pi times the diameter, right? All right, so really important that we remember and understand what pi is. So pi is not just some arbitrary number that someone came up with. It's been year after year. I mean, you can trace it back hundreds and hundreds of years into history. Maybe even a couple thousand years, if I'm remembering correctly, where they didn't have exactly it calculated, but a lot of ancient mathematicians had approximations of it, where they were taking the, again, circumference of a circle, dividing it by the diameter, and getting an approximation of what that would be. Okay, so that's what pi is, and pi comes into play a lot here with what we're talking about. So like we just said, we can rearrange that to find the equation of a circle. That's what I was just saying there, right? By rearranging it, we can say pi, the circumference, is equal to pi times the diameter, right? By rearranging that first equation. Or, since the diameter is just 2 times the radius, we can write it as 2 pi times the radius. So this is important because let's think back to our unit circle. Again, simple but really important. What is the radius of our unit circle, right? All right, so it has a radius of 1. So if the radius is 1, right, what is the distance around our circle, right? So circumference is 2 times pi times the radius. Well, 2 times pi times 1 means the circumference of our circle is 2 pi. Now this is going to be really important because when we're talking about, and we're going to talk about this in a second, what are called radians, that is measuring around the outside of a circle. Think about our circumference, right? If I start from here and I go around this circle and I measure the length. So imagine a piece of string, right? And we went around that circle. How long is that piece of string? It's going to be 2 pi because the circumference is 2 pi. So if I took that piece of string and laid it out, right, pulled it out straight, that's how long it would be. It would be 2 pi. That's the length. Now, 2 pi is a nicer way of saying, instead of getting out our calculator and going, all right, well, what's pi and what's that times 2, right? So what's 2 times pi? That's about 6.28, right? So 6.28 units approximately, right? So keep this in mind as we do this lesson. This is going to be really important. We use pi instead so we can avoid writing these ugly decimals down. So when I say 2 pi is the length around the circle, it's just a neater way of saying it instead of saying 6.28 approximately. All right, so that's what I got over here, right? Setting the radius equal to 1 like we just said, right? The distance around the circle. It has a radius of 1 unit. And if we set the radius equal to 1, right, that tells us that the distance around the circumference is 2 pi. All right, so let me just clean this up a bit here. And let's talk a little bit about some more distances around the circle. All right, so if it's 2 pi to get all the way, you start at 0, right? And then it's 2 pi to go, if you go this way and travel around all the way around a circle. Well, what would halfway around the circle be? That would be pi, right? Cut the circle in half, cut the distance in half, right? If it's 2 pi to go all the way around, it's pi to go halfway around. And I could cut that in half again. Well, what's half of pi? Well, instead of writing as a decimal, it's just pi divided by 2. That would be a quarter of the way around. And we could keep cutting up a circle this way over and over again. And that is a big part of what we're going to do in this lesson, is chop this circle up into a lot. So measuring around a circle is called, the lengths that we measure are called radians, okay? So why do we call it a radian? Well, it comes from the word radius. Because the idea is, again, think about our radius here, right? We have a radius of 1, right? Let me just draw that in a different color so I don't mix it up. Or let me just get rid of some stuff here. All right, so it's a radius of 1, right? That is our radius. So if we take that, again, take that piece of, a smaller piece of string, right? Imagine that here's our radius of 1, right, from end to end. And what if we bend that around our circle? So I'm not going to do the greatest job here, but imagine I took that piece of string, that little red piece of string, and I wrapped it around the circle. So let's say it goes from there to there. And that's 1, right? We'd say that's 1 radian. All right, so, and it had, again, there's our radius of 1, right? So 1 radian. Now, a radian is not anything special. It's just a regular number. We just use the word radian because we're implying that it's a measure taken from the radius. So we got some really important stuff here to learn about. Again, a radian is the length of an arc going around the unit circle, right? So that's this arc right here as we arc as we go around. So when we're measuring the length around the outside, we call that a radian. It's defined by taking the radius of the circle, which we did, and wrapping around the circle. So that's what I just did right here, right? All right, so we just said a full unit circle has a circumference of 2 pi radians, right? Because it's 2 pi to go all the way around it. Now this is a standard unit. That's why I have an SI, standard international unit for measuring. So if those of you are going to continue in math or engineering, etc., have to get a pretty decent grasp on this. And I don't expect you to have it all in one day watching one video, but this video is really to start setting the foundation of getting to know this. So I'm going to jump over to just a little like a mini video here and talk a little more about radians. Okay, so see, there's our radius. So this is going to draw a circle. We're going to watch this a couple times. And there's our radius r, right? Which is generally 1. So now imagine you take that and you wind it around the circle. So look, there's what it would look like there. And we call that 1 radian, right? That red line there, right? And the green lines, because that's 1 radius. Now look as you extend it, 2 radians, 3 radians. And then remember we said half a circle was pi radians, like 3.14. So a little more than 3. And then we could double that up to do a full circle, right? All the way around would be 2 pi or 6.28, right? So that's the distance around the circle. But to avoid using decimals, we use pi instead, right? So again, pi is half a circle. So let's watch that one more time. Again, there's our circle. It has a radius of 1. And the radian is just taking that radius and measuring around like a piece of string that we can measure around the outside of the circle. So 1 radian, right? And then 2, and then 3, and then you need a little bit more to make it to a full half circle or half circle, right? So that's where you get pi, because pi is 3.14, a little more. And then you can keep going around 2 pi to make a full circle. So this part is really important to start getting the idea of a radian, right? Measuring around the outside of a circle. Okay, so that little video really tries to demonstrate, and I would encourage you to watch it often because it really helps hammer home the point of what a radian is. Remember, it's just measuring around the outside of a circle. But a circle, like we said, I know I might be repeating myself, but it's really important. To get around a circle, it's 2 pi, right, to make it all the way around. So 2 pi is not like a nice number. It's 6.28, like we said, right? So that's why we're using pi instead of writing that. So the idea, again, like there's 1 radian. There would be 2 radians about, right, to there. Here's about 3 radians to there. And again, I'm just doing an approximation of that video, right? That's 3 radians. Now the radians are this part here. 1, 2, 3, right? And they're all 1 unit long. It's just this 1 unit, but if we bent it, right, like a piece of string. That's the way to kind of think about it, like a piece of string. Now, you may also hear this called like the winding function, the idea of winding around the outside, like a piece of string winding around the unit circle. It's the same idea, right? It's the exact same math. So we're taking that, we're winding around, and then it takes this part here a little bit more. It takes that like 0.14, of pi, right, that extra part of pi to get to half a circle, right? And don't forget, because our unit circle is 2 pi. So again, if you cut that in half, right, this is a pi, right, and this is a pi, measured around the outside. Okay, so that's really important there, okay? Now, let's talk a little bit about degrees, because that's what we're all mostly comfortable. I know when I was your age, degrees were much easier. That's what we've grown up using, right? The idea of taking a circle and cutting it up into 360 portions, right? So that's what most of us are probably pretty comfortable with, right? A degree. So with degrees aren't lengths though. Degrees are units of rotation. That's the difference. So the idea of a degree, and I'm getting a little sloppy here, but the idea of a degree with our unit circle again is, sorry, a really bad circle. That is the worst circle ever. That one's not much better. But the idea of a degree is there's a starting point and an end point, right? So this is your starting, this is your end, okay? And we'll put some more fancy definitions on those words in a minute. Okay, and rotating from here to here is a degree, right? So maybe you go 30 degrees or 40 degrees, right? The idea of rotating. So rotation, like the arms of a clock. So these two ideas of degrees and radians actually coexist in the same world. But we got to keep this in mind, okay? So big thing to remember is a degree is rotation, okay? Degrees are defined by rotation, how much you rotate, okay? The radians are the length around the outside. Now they coexist at the same time, okay? We can talk about rotating to get to this point, or we can talk about the length traveled along the outside to get to this point. And so imagine a point on our circle, XY, right? There's two different ways of describing it, either rotating to get there or the length around the outside to get there. Now, 360 degrees kind of goes back to ancient times. I won't bore you on the history lesson of where people think it comes from, but it generally is equated to the number of days in the year, pretty close, right? 365, that's where a lot of the belief comes from. It's not a standard international unit though, okay? So most mathematicians, when you get into really fancy math, you want to go work at NASA or you want to do stuff accurately, they don't use degrees, they use radians, okay? Radians are very accurate, very specific, okay? Now, you're probably more used to degrees though. So the thing is, when you start out, it's probably really helpful to be able to convert back and forth between them, and we want to know how to do that. So let's talk about how to convert between degrees and radians. It's really easy. So if I got something in degrees, like 65 degrees, let's make this even easier. Let's, instead of 65, I'm going to make it 60 for now, okay? I'm going to change this, make it a really simple one. All right, so if I got 60 degrees, and I want to convert it to radians, all I have to do is times it by pi over 180 and reduce, okay? So there we go. So I'm going to go, all right, well, what's 60 divided by 180, right? So 60 and 180, hey, we can reduce that pretty easy. 60 goes on itself once, 180 is divisible by 63 times, and I get pi over 3. There you go. So that's what it would be in radians. Now, we don't have to write rad next to it to say that's in radians, because like I said, radians are just standard numbers, okay? Notice with degrees, anytime we're referring to degrees, though, we have to put that symbol there. So now, what is pi over 3 in decimal form, right? Okay, well, let's get our calculator out. Let's go, what's pi divided by 3? And we can get the decimal equivalent. It's about 1.04, right? So approximately 1.04. So our diagram, right, if this was 1 radian from here to here, right, it's a little bit past that. All right, so there we go. But that's why we prefer to use this. We write it this way. So 60 degrees is pi over 3. All right, the next one, 1.75 radians. So where is 1.75? Well, we said 2 is kind of like over here. So if we want to write as a decimal, it's right around there, right? 1.75 maybe, approximately going by, right? 1 3/4, right? All we got to do is times it by 180 over pi. So what's 1.75 times 180 over pi? Well, I'm going to go, what's 1.75 times 180? It's going to give me 315 divided by pi degrees, right? Now that's kind of ugly, right? So in this case, I probably would write, that's an exact degree, right? But if I want to write as a decimal, it's approximately 100.3 degrees. Right, so like we said, a little bit past 90. Now that's not the best example because like I said, we usually don't work with radians too much in decimals, but I want to do one in decimals. Let's do one more. Let me just give you a radian. So I'm going to make up one here. Let's go, how about, let's convert 5 pi over 4 radians. And you go, well, where is that on the unit circle, right? This is a better example than the last one. So how do we convert it? Times it by 180 over pi. All right, so again, the pi's cancel out, right? So that eliminates that, where in this case, I didn't have any pi's to cancel, so that's why I said this wasn't the best example. This one is more what we're going to be working with. And then I can go, all right, well, what's 5 times 180 divided by 4? All right, so 5 times 180 divided by 4, what are we going to get here? 225 degrees is what I got. All right, so there we go. So this is a better example. Really should have started with this one. Here we go. 225 degrees. So now you might have an easier time finding that in your unit circle because you know, okay, 180 is a half a circle, right? So it's somewhere past 180, so it's somewhere down here, right? So that's going to help us find things. So keep this in mind. I know this is like a little part of the lesson, and this is where a lot of you, if you remember this when we get into the other parts of the lesson, we'll have a much easier time. Don't forget this, okay? To convert back and forth, especially this one, to convert radians to degrees. This is the one I think all of you are going to need for today's lesson, okay? It's probably the most important part of today's lesson because working with the radians, if it's your first time, is probably going to be the biggest hill to get over. And to help you figure out where stuff is, just times it by 180 divided by pi. All right, so for example, remember we said 1 radian right here, right? 1 radian is right here. Well, how many degrees is 1 radian, right? So what's 1 radian equal in degrees, right? Well, what do I have to times that by? Like we said, if that's radians, let's times it by 180 divided by pi. Well, 1 times 180 over pi is just 180 divided by pi. So let's get out our calculator. Okay, and let's go, well, 1 times 180 is 180 divided by pi. Boom, what do we got? 57.29, so we'll say about 57.3. So 1 radian is about 57.3 degrees right there. So that's the kind of tricky thing with this. Going back and forth between radians and degrees, you tend to get a lot of messy numbers, right? Like it doesn't, 1 radian is not equal to 1 beautiful, perfect degree. Like it doesn't land right on 90 or 50 or something like that. It lands on 57.3. And vice versa, when you're doing something like 60 degrees down here, hey, that's a real nice number, right? But when you convert it to radians, yeah, you get pi over 3, which is okay to write, but you also get a decimal like 1.04. So converting between the two is kind of messy, ugly number business, right? Not hard to do, just you don't get nice numbers, so don't be surprised about that. All right, let's move on, and a lot of important information on this first page. Like if this had been in class, we'd be talking about this every day, all week. I'd be bringing this up at the start of class and reviewing all of this stuff. This right here, this lesson is long, but this whole thing is key, and it's really important. I'd be talking about it over and over and over again, where now it's just one video, right? All right, moving on, we're going to continue talking about what we're talking about, and a lot of focus is going to be on radians, and I'm going to always try to equate or relate this to angles, okay, so that we can get a real good grip on it. So we got our radian measures and our angle measures, right? Okay, so now, again, what is a radian? Again, like we said, imagine taking a piece of string and wrapping, okay, and that string could be any length right now, not just one, right? Now, one was that piece of string when it was just our radius. But imagine we just keep going, make that string longer, like 2 radians or 3 radians or 4.67 or some number, any length, okay? We're going to wrap it around the unit circle. What we're interested in finding today is what point on the circle would that piece of string end at or terminate at, okay? So we call that a terminal point. So the terminal point, coming from the word terminate, right? All right, so what we generally do is most textbooks like to use the variable t to represent that real number, that length, okay? So this is going to be a real number, will be the length that we wrap our piece of string around. Now, for both, I got a lot of the stuff under radians, but it should be for both. I know I have angles down here. The angles is just sort of adding on, okay? Everything starts at 1, 0. So that's right here, okay? We call this standard position, okay, for whether it's degrees or radians or whatever. This is standard position. This is our starting point always, 1, 0. And this is what we might call our initial arm, okay? So I'm just going to label some stuff here. So if you see the word initial arm, meaning the length here, right? Initial arm, not the length, but the arm, the actual line there, okay? Starting, or the ray starting there at 0, 0, right? Like the arm of a clock, right? And going through 1, 0. That's our initial arm. All right, so when we're talking about a radian, right, we're talking about that piece of string that we measure around the outside. So imagine something like this. I'm just going to draw. We don't know how long this is, okay, but we'll just say, imagine it takes us, around. Here's this length. I've hit here. I keep going. Okay, we'll say we stop right there. Okay, so t would represent the length, okay? T is that radian length. So usually we use pi, and things like that, numbers involving pi, I should say, to describe the length. Like we said, 2 pi was a full circle, right? We can also write it as a decimal, but writing it with pi helps us be more accurate. All right, so the place we end at, okay, is called our terminal point. So right there. So we're going to end up at a coordinate, an x, y coordinate. That's what we're really into for the next few days. Where is that point? Okay, where is that terminal point? Okay. Now, where it ends at, that line, remember we had our initial arm, okay? The line going through this, again, I should be using a ruler here, but it's hard on the computer, right, is called our terminal arm. So I'm really squishing everything in here. Terminal arm, right? So like another arm of a clock where it ends, except we're going counterclockwise as we rotate, right? All right. Now, if we want to talk about degrees, right, that would be measuring an angle, the amount of rotation. And usually we like to use the symbol theta, right? We usually like to use the Greek letters for that, right? So theta, we'll use that for now. It could be anything, but theta is the most popular one. It looks like a little Pokeball, right? That's our rotation, right? How much we've rotated. And rotation is generally measured in, again, degrees. Okay, so there's 2 different ways of getting to that. A degree measurement, how much we rotated, or the length around that circle. All right, now, if we're headed in the counterclockwise direction, that's when t is positive. Okay, so if t is a positive number, oops, hang on, let me just keep my colors coordinated. So if t is positive, we're heading this direction, right? And same thing if our angle is positive. So if we have a positive angle, okay? So if they're greater than 0, that means we're always headed in this counterclockwise direction, okay? Now, if we head in a clockwise direction, that's when t is negative, or our angle is negative. So now, when we make it negative, that doesn't mean the length itself is negative, but it's implying that the way that we are moving is negative, okay? We're moving in a negative direction. So this has direction, or same thing with the angle. It's implying that the amount of rotation is moving in the negative direction. Okay, so that's the focus. Today's big focus is, what's this point? Where do we end at? And finding key points, okay? So again, like I said, this is a really long lesson, but it's just jam-packed with some of the most important stuff, not just for this unit, but going forward. This is really all about big concepts, new terminology, and I don't want to skip over it and just say, we'll just move to the easier stuff that's easier to mark and do homework-wise, because I'd really be hurting you without getting you some understanding of this, okay? Now, what about coterminal angles? Coterminal angles are angles, or coterminal radian lengths, okay, are ones that share the same initial arm. They start here, right? And they end at the same place, but they might move in different directions, or you might go more. So for example, let's start with I'll just do some examples here and explain as we go. So a coterminal angle, or coterminal radian, might be moving the negative direction. So let's say we moved in the positive direction to get at this point, right? Well, what if I went the other way around? What if I went the negative direction to end up right there, right? I still end up at the same terminal point. So we would call that a coterminal angle, or a coterminal radian. I don't know why I left the word radian out of here. There we go. So that's an example of a coterminal one, going the opposite direction but ending at the same place. Another example of a coterminal angle or radian is, what if we went around more than once? What if let's just think about degrees for a minute. What if we went around 360 degrees, right? And then what if I kept going over a full circle, right? And I ended there. That would also be a coterminal angle. So for example, around, and then I stopped there, right? That's called a coterminal angle. We ended at the same place. We did a full circle and then a little more. And you could obviously do that infinitely, because you could go around again and end up the same place. And then around, keep going, right? You could just keep going and going and going and keep ending at that same arm. And you could do that in either direction. So coterminal angles, long story short, is an angle that goes in either direction but ends at the same place, okay? All right, so let's move on, and what we're going to start doing now is finding some key points on this unit circle. So I know this is a little draining, but it's all super important stuff. Okay, so let's start by cutting our unit circle up in points that we already started with. So we already know the radius is 1, right? So recall, if the radius is 1, then I know these 4 key points. I know that this point right here is 1 over 0 up, and I know this one over here would be negative 1 over 0 up, right? Because that's our radius. From here to here is 1. And same thing going the other way from the center. Okay, at the top, we would have 0, 1, and at the bottom, we'd have 0, negative 1. So these are our first 4 key points that we want to know. Now, there are infinite points on the unit circle. We are going to zero in on a group of key points that are really essential when you first start learning this, that are very common. If you look up unit circle on the internet, you will see all the key points listed that I'm going to go through, okay? All right, so let's talk about, though, the main thing is how do we arrive at them, right? All right, so let's talk about degrees. This is 0 degrees. Like if we're starting right here, here's our initial arm, starting right here, then we're at 0 degrees, right? Or if we write as radians, I'm not writing this as a set of points, I'm just putting a comma between it. Radians would be 0 radians. All right, well, if we travel all the way around the circle, right? So what's the length? Remember we said our unit circle, 2 pi times the radius. Well, if the radius is 1, 2 times pi times 1, right? Let me just remind you of that, right? This is where this all comes from, right? 2 times pi times the radius is the circumference of a circle. Well, the unit circle has a radius of 1. So the circumference is 2 pi, right? So to go fully around the circle, from here to here, the length would be 2 pi. Well, how many degrees is a full circle? That we're probably more comfortable with, is 360, right? Well, let's start cutting this thing up. All right, so that brings us to this point here, right? Let's cut it in half. 360 cut in half is 180 degrees, right? And 2 pi cut in half is pi. Well, let's cut that in half again, into a quarter of a circle, right? 180 cut in half is 90 degrees, right? Oh, I forgot my little degree symbol there. Pi cut in half is pi divided by 2, right? So we're going to write it as pi over 2 instead of a decimal, right? All right, so now, what about down here? How are we going to figure that one out? Well, we already know that going from here to here is 1 pi over 2, right? From here to here is 2 pi over 2, right? Because that's another quarter. Well, what's 2 pi over 2? That's just pi. That's that. Well, let's go a little further. That means from here to here must be 3 pi over 2. Right? Because each pi over 2 is a quarter of a circle. 1, 2, 3. And if you get back to here, coming all the way back around, that would be 4 pi over 2. Well, what's 4 pi divided by 2? That's just 2 pi, right? So everything works out. It checks out. It makes sense. The math is good. All right. Let me get rid of this stuff. And counting by 90s, right? 90, 180, right? Because 90 plus 90 is 180, plus another 90 is 270, okay? So there's our first group there. So for some example questions, just to start off, a question might say, all right, give me the terminal point when theta equals 180 degrees. Well, that's pretty easy, right? It is negative 1, 0 right here, right? Or give me the terminal point when t, which is our distance around the outside, is pi over 2, right? That's pretty easy. What do we got? Pi over 2 is 0, 1. What if it's something like this? What if someone said, give me it when it is, let's do 720 degrees. Well, you go, wait a minute, that's not on our circle, right? But I can find more by subtracting 360 from that, right? Because that's a full circle, right? So why don't we take 720 and subtract 360, and what do we end up at, right? Obviously, we're just going to be at 360, right? Because that's 2 full circles. So 720 minus 360 is just 360. So I've done, in other words, if we're doing this in angles, I've gone around 360, that's one circle, and another 360 brings me to 720, right? So the answer would be 1, 0. Okay, and we can do the same thing with radians. Let's do another one with degrees, though. What if I gave you 900 degrees, okay? Because that's where we're more comfortable with to start. So I really want to focus on that, and then we'll convert and talk about radians, okay? 900 degrees, well, how many circles is that? We know 360 is 1 circle, 720 is 2 circles, so why don't I subtract 720 from that, and what do we get, right? We get 180 degrees. So in this case, this is like going around 2 full circles, right? 360, again, 720, and then 180 degrees more, and where do we end up at? At the terminal point, negative 1, 0. All right. Now the same thing can be done with radians. So instead of pi over 2, what if I said, or like 3 pi over 2 or something, let's say I go 5 pi over 2, right? I say t equals 5 pi over 2. tell me the terminal point there. There's a couple ways we could do it. We could just count, right? Or we could subtract 2 pi from it. So, because 2 pi is a full circle. So if I go, well, what's 5 pi? Take away a full circle, what do we end up at, right? 5 pi over 2 minus, if we get a common denominator, this would be 4 pi over 2. That leaves me with 1 pi over 2. Well, there's that right there. That's a quarter of a circle, right? So the answer to this would be 0, 1. That's the terminal point. Or, instead of subtracting 2 pi, I could have just counted by pi over 2's, right? What do I mean by that? 5 pi over 2, couldn't that just be rewritten like this? Isn't that just 5 times pi over 2? That's what 5 pi over 2 is, right? It's 5 pi over 2's. Well, look at our unit circle. Every pi over 2 is a quarter. So we go 1 quarter, 1 pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2, 5 pi over 2. That's where 5 pi over 2 is. And we end up at the exact same answer I just got down here. Okay? So it's the same idea, except with a circle, we're going in 360s. In radians, we're going by pi over 2. So you can subtract, or you could just count around like that. Okay? Okay, so what do we mean by cutting a circle into eighths? Let's think about it. What I mean is, this was a quarter right here, right? That's a quarter of a circle. Well, what if we cut that in half? That would be an eighth. So like here, starting at 0, 1, 2 eighths, right? 3 eighths, 4 eighths, 5 eighths, 6 eighths, 7 eighths, and we're back to 8 eighths. So we've cut it like a pizza, right, into 8 slices. So let's think about that. What is that in degrees? We already know. I'm going to draw a line through here because I'm going to talk about this in 1 second. So what I'm going to do is draw the line y equals x through here because this is going to be key in a minute. If I could line it up a little better with my eighths, that would be cool. All right, that's going to be as good as we get, I think, there. So my eighths, they might be off by just a titch. No, this one's not. Nothing like watching me draw a circle, eh? I mean, nothing like watching me draw a line. Okay. So how many degrees is that? We know that this is 90 here. Let me write in the key ones again, right? We know that this is 90. This is 180 in degrees. We know that this is 270 in degrees. And we get back to 360 or starting at 0, right? 0 or 360. All right. Well, let's cut that in half, right? Degrees are the easiest, right? So half of 90 is 45 degrees. So that's the easiest way for us to start thinking about this. 45 degrees, right? So let's write those in, right? So this is 45, right? I'll put that right over here. I'll just put it at the end of this line here somewhere, or right here. 45 degrees, right? Plus another 45 is 90, plus another 45 would be 135 over here, plus another 45 is 180, plus another 45 would bring us to here, which is 225. Plus another 45 is 270, plus another 45 is 315, plus another 45 brings us back to 360. So cutting up in degrees is pretty easy. It's not much harder to cut it into radians. What did we say? We already said this is 0 radians or 2 pi. Well, remember how we cut that in half and said that this is pi radians. Well, we cut that in half and said that this is pi over 2 radians. So what if we cut that in half again? Well, what would 45 degrees be in radians? Cut that in half is going to be pi over 4. Or, and remember this was from the first page of the lesson. I know you're already zoned out. Maybe you have to take a break and come back. How can I convert anytime you're stumped, anytime you're like, wait a minute, how do I make that into radians and you want a quick way of doing it? Times it by pi over 180, right? Just times it by that. So what happens here? 45 goes in itself once, it goes into 84 times. What do you get? Pi over 4. So remember that. This here is so important for this lesson when you're first learning this, okay? To convert really quickly. So if you're ever stumped, times it by, the secret is pi over 180. So I could take all of these and go, all right, well, what's 135 times pi 180? What's 225 times pi over 180? But there's an easier way. Why don't we just count by pi over 4s? 1 pi over 4 is here, right? 2 pi over 4s is here. Well, what's 2 over 4 reduced to? Pi over 2. Check, we got that one. 3 pi over 4 is over here, right? Now remember, that's how much we've traveled around the outside. 4 pi over 4 is here, but we already got that because 4 pi over 4 reduces to pi. So we already got that covered, right? All right, then we get to 5 pi over 4 is down here, right there. Let me just write this kind of below. I know it's getting a little sloppy. 5 pi over 4. Then we get to 6 pi over 4 here. Well, what's 6 pi over 4 reduced to? It reduces to 3 pi over 2, which we already had in our earlier one. And then we get to 7 pi over 4 right here. right? Which is this guy here. And then we get to 8 pi over 4. Well, 8 divided by 4 is just 2 pi, so there you go. So there is the radian measurements and the degree measurements written together. And that is key about this unit, is really trying to get that down pat. Now, the main thing is we need to figure out these points. What is this point? Let's start with this one right here, right? What is that point right there? All right, so what is this point? What are its coordinates? That's what we need, right? These ones were easy, right? When it was like 0, 1 and 1, 0, that was easy. These are a little more confusing, right? They're gonna be ugly decimal numbers. But there's a way of finding them and writing them without using decimals. And we're gonna use radicals. So here's what we're gonna do. Remember that triangle that we talked about? Remember how we had that triangle? Let me just draw him in here, right? Here he is, okay? So let's take this triangle out. And there's a couple ways of doing this. I'm gonna take this triangle, I'm gonna draw it outside of the unit circle and we'll talk about it. All right, I haven't done the best job of it, but here we go. So this triangle has a 45-degree angle there, right? Well, what's the top angle then? This triangle up here, or this angle up here would also have to be 45 degrees, right? For it to work, because we got a 90-degree corner here, and there has to be 180 degrees in a triangle. Okay, so we know that. So this is an isosceles triangle where these are the same length, right? So let's just call those lengths x for now. We'll just say this is x, and what's our radius? Our radius here is 1, right? Now, if you're like, well, shouldn't it be y? It doesn't matter in this case because they're the same length. That's all I really care about. What's that length, right? They're gonna be the same. So in other words, once we figure out what this point is, the x and y coordinate are gonna be the same because the length going from here to here is gonna be the same as the length going here to here. They're gonna be the same length, right? All right, so, well, let's set up Pythagorean theorem, right? Doesn't Pythagorean theorem say x squared plus y squared equals r squared, or a squared plus b squared, whatever you want, whatever variation of it you want to use, it's the same thing, right? Equals c squared. All right, let's sub everything in. X squared plus x squared equals 1 squared, right? Well, x squared plus x squared, that's 2x squared. 1 squared is 1. All right, so now I just got to solve for x. Let's divide both sides by by 2. We get 1/2, and then we're going to take the square root of both sides, right? All right, so we're going to have plus or minus the square root of 1, which is 1, and the square root of 2, which is root 2. Now, remember, we have to clean this thing up a little bit, though. Anytime we have that radian on the bottom, that radical symbol on the bottom, we want to get rid of it. So how are we going to do that? We're just going to multiply this thing by root 2 over root 2. And we end up getting our x value, and I'm just going to ignore the negative for now because we're just talking about the length of this, okay? So we're going to ignore the negative. We're just going to keep the positive. Is going to be root 2 over the square root of 4, which is 2. So that is the length of each side of this triangle. So this side is root 2 over 2, and this side is root 2 over 2. They're the same length. So that means these coordinates, the mystery coordinates, are root 2 over 2. Now, what is that as a decimal? We're going to see quickly why we'd prefer to write root 2 over 2, because if I take 2 and then I square root it, and then I divide that by 2, it's really 0.7071, right? It's a horrible number. It's a lot easier to write this. But just to be clear, it is approximately 0.707. But again, so much easier to just write it as a radical. All right, so there you go. Now, how can we find the other points? This thing's like a mirror, right? This point here, this point here, this point here, they're all really the same thing, just with switching where the negative is and the positives are. Because if we draw a line through here, right, it creates this mirror image, right? It's symmetrical. They're congruent triangles. So essentially what I'm saying here is the distance from here to here, right, if we draw it this way, is exactly the same as the distance on the other side, and the distance going up is exactly the same there. And then you could do the same thing for these triangles down here. Now I'm making a real sloppy mess of my my diagram here, but all that ends up happening is it's the exact same points, except in this case down here the x is positive and the y is negative. Over here, up here, this point, sorry, it's getting super sloppy, the x is negative but the y is positive, and down in the third quadrant right there, the x coordinate is negative and the y coordinate is negative. But the lengths are the same, so that's why I can just make them the same points. So we just found 4 more key points, right? We got this one, this guy here, and this guy here. So I went through this to show you how I can find them. Now don't forget, we already have some key points here, 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 and here. So now we've got 8 key points. We just got to go a little bit further and find a few more, and then we're going to finish up with our with our unit circle with lots of points on it, okay? So that's how I can find basically the 45-degree angles or the pi over 4 angles. Okay, going into the last set of key points, what if we cut this circle into 12ths? So I'm going to take each quarter and cut it up into 3 pieces, right? So here's our first quarter. We're going to cut it into 1, 2, 3 pieces, right? And then we can do that again. 4, 5. Sorry, that's not very well cut. I'm trying to freehand it. 4, 5, 6 pieces. 7, 8, 9 pieces. 10, 11, and then we're back to 12, right? So that's where we're cutting it up. So if we were talking about degrees, this would be, again, imagine we're starting at 90 degrees. I'll just put it, where can I write this here? Here's 90. I'm going to write it way up here. 90 degrees, right? I'll just do the degrees for this one. Then when I get to the very end, I'll write the radians in so I don't muck it up too much. So that's 90, 180, right? 270, 360, coming all the way around, right? Or starting at 0. So in other words, if we take 90 and cut it into thirds, this here would be at 30 degrees, right? And this would be at 60 degrees, and so on and so forth. You keep counting around, right? 90, 120, 150, 180, keep going. Okay, so here's how we're gonna make this happen. What we're gonna do is we're just gonna focus on the 30 degree mark, and we'll say, I'm a little bit off here. We'll just say, okay, there's my 30 about. All right, so that line does not look so good. Let me try that again. Okay, so I drew a line from 0 to 30 degrees, right? And that would be a 30-degree angle there. Now here's the catch. So I said create an isosceles triangle from the origin from 30 and negative 30. So I'm going to draw another line here starting at the origin to negative 30 down here. So that would be moving in the negative direction, right? 30 degrees, and we get another 30 degree, right? So this would be moving negative 30 degrees, but I'm just going to write 30 in. So what we got there is 60 degrees, right? All right, so what we end up having is an isosceles triangle, because don't forget our radius is 1, so the length here is 1. The length here is 1. What I can do is connect these up, and this length will also end up being 1. Oops. All right, so we got this here is 1. So really, this, if I just take this triangle out, this is 60 degrees, and all the corners are 60. This is 60, this is 60, and this is 60, and that's what I've done. So what I'm going to do now is I'm just going to focus on half of this triangle. What if I just take this here? Okay, back to half again. So I'm going to take that out and draw that triangle. All right, so there's that triangle. We got a 90-degree corner right here, right? And that's 30 degrees there. That's 60 degrees up there, right? That would make sense. Now, how we know this side here is 1. We don't know how long this side here is, but we do know the height is 1/2. Because if this is 1 all the way down, then half of that would be a half. So in other words, we just figured out the first part of this point here, right? This point here, the y-coordinate is 1/2 up, right? That's how far it is from here to here, half of 1. So all we got to do is figure out the x-coordinate. So let's sub this into Pythagorean theorem, or x squared plus y squared equals r squared. It's the same formula. And we're just going to solve again. So I'm going to go x squared plus a half squared equals 1 squared. All right, and let's try and do this quickly, right? So we're going to square 1/2, which is going to give us 1/4. We're going to move it to the other side by subtracting. So we're going to have 1 minus 1/4. We're going to get common denominator. Instead of making this 1, make it 4/4. So we're going to get x squared equals 3/4. We're going to take the square root of both sides. And we end up with the square root of 3 over the square root of 4, and the square root of 4 is 2. And there you go, and it's going to be plus or minus, but we're just going to look at the positive one for now, and there you go. So the x-coordinate here would be √3/2. So we just found it. So now, using symmetry, right, this and this one, they'll all be the same point. In other words, here is going to be x is √3/2, y is -1/2. I can come over here and go, well, x is -√3/2, y is +1/2. Sorry, that's an ugly 2. Down here, x would be -√3/2, and y would be -1/2. So we just found 4 more points, right? Now, without boring you to death, we can do the exact same trick by drawing a triangle up here. right? I could do this triangle where there's 60 degrees here, and I could do the exact same thing, except the triangle would look more like this if I cut it in half, right? So, sorry, that's really sloppy here, right? There's that angle there, and guess what? This is 1/2 across, and if we solve for the y-coordinate, you end up getting √3/2. So this point right here ends up just being the coordinates flipped. It's 1/2 for the y, and √3/2 for the x. And then using symmetry, we can find all these other points. So I found that other one really quickly. I'm not going to go into detail because you can really just do the exact same math. It's the same triangle just flipped around, right? It's a congruent triangle. So the x coordinate here would be -1/2. Y would be √3/2. All right, and we get 1/2 -√3/2. And -1/2 -√3/2. So we just added a bunch of points to our unit circle. Now the good news is we're through the meat of this lesson. We just need to go label our big unit circle and really get kind of familiar with these points, okay? So let's do it. Okay, so if you are looking for this, again, you can find a filled out one of these. They're all over the internet, just looking for the unit circle, but it's really important that you know how to fill one out yourself. If we were in class, we'd really be focusing on this. It would actually be one of your quizzes, as I basically give you a blank one and can you fill it out, right? Okay, so how do we do that? Well, first I start at 0, right? So I'm going to put the radians here. 0 radians or 0 degrees, which is 1, 0, right? And now if we travel all the way around the circle, right, we get to 360 degrees of rotation, or the length around the outside is 2 pi. Now, what do I do next? I cut that in half, and I go, well, what's half of 360? Half of 360 is 180 degrees, right? And what's half of 2 pi? It's pi. And that's how I get to -1, 0. So when people say, well, how do I memorize this? This is basically what I'm walking you through it. And then I cut that in half, right? Half of 180 is 90 degrees. And then half of pi is pi/2. All right, so we've cut that in half, and that's 1, 0. And then I just count around by quarters, right? Like you go 0, 90, 180. This would be 270, right? And same with your radians. You have 0, then you go 1 pi/2, 2 pi/2, then you get down here to 3 pi/2, right? So if we're counting by pi/2s, right? There you go, that's 3 of them. Because if you get to 4 pi/2, remember this would be 4 pi/2, which is just 2 pi. So I'm just counting by pi/2s. All right, so we got those ones filled in. Oh, and let's not forget these points down here. 0, -1. All right, so there was our first set of key. All right, let's move on to our 45-degree angles, right? So remember we took 90 and cut that in half. So 90 cut in half was 45 degrees. All right, well, what's pi/2 cut in half? That's pi/4, right? Now, let's count by 45s first because we're probably more comfortable with that. So 45, 90, 90 plus another 45 is 135. 135 plus another 45 is 180. 180 plus another 45 is 225. 225 plus another 45 brings us down to 270. 270 plus another 45 brings us to 315. And then plus another 45 brings us to 360. Okay, so we've done that. And what about the radians? We're counting by pi/4. So think about it, like 1 pi/4, 2 pi/4, 3 pi/4, right? 4 pi/4. Etc. Right? Now, again, these reduced. 2 pi/4 is just pi/2. 4 pi/4 is just pi when I reduce it. So that's what I'm going to count. 1 pi/4, 2 pi/4, 3 pi/4. So some of these are already labeled because we already labeled them when we were doing the pi/2s, right? Our quarter of a circle. All right, then we get to 4 pi/4. We already got that. Then we get to here, 5 pi/4. All right. Then we get down here to 6 pi/4, which reduces to 3 pi/2. We already have it. Then 7 pi/4. And then you get to 8 pi/4, which just reduces to 2 pi. All right, so we got those all in. Now let's write in those key points. So the key points we found for that are √2/2. Now, remember, before I even go any farther, let's remind ourselves, right? In this quadrant, in quadrant 1, the x's are positive, the y's are positive. In quadrant 2, the x's are negative, the y's are positive. So it's just symmetry, right? After this point, you only need to know the first quadrant, and then you can just basically use symmetry to find the rest. In the third quadrant, both coordinates are negative. And in the fourth quadrant, the x is positive and the y is negative. So when I fill these in, it's the same points, except I just change the sign. So -√2/2 and √2/2 down here, -√2/2, -√2/2, and finally over here, x is positive, y is negative. All right, let's get to the final group here, the 30-degree angles, okay? and 30s and 60s, right? So let's count by 30s. Remember, if we take 90 and cut it into thirds, right? 90 divided by 3 is 30 degrees. So we got 30 plus another 30 is 60 plus another 30 is 90. So we already have that. Plus another 30 is 120. Keep adding 30s, 150. You get to 180. We already got it. 210, 240 plus another 30 is 270. We already got it. 300. 330, and then you're back to 360. Now, what about radians? Okay, so what are we going to do? This one I didn't do on the unit circle, so let's think about this. How am I going to calculate this? This one I didn't do when we did the example. I said I'd save it till now. So let's start with pi over 2. Well, I want to divide that by 3, right? So if I divide that by 3, it's the same as timesing it by a third. So what do we get? We get a pi over 6. So that means this is pi over 6. So all we're going to do is count by pi over 6's, right? 1 pi over 6 is 30 degrees. 2 pi over 6, right? 3 pi over 6. 4 pi over 6, and so on and so forth, right? 5 pi over 6. Now remember, some of these are going to reduce, so they'll look different, because 2 pi over 6 is just pi over 3. 3 over pi over 6, 3 pi over 6 is pi over 2. 4 pi over 6 is 2 pi over 3, and so on and so forth. So this is 1 pi over 6. This here is 2 pi over 6, which is pi over 3. So I'm just reducing. Then we get to 3 pi over 6, which is this guy, right? Pi over 2. So we already got him. He's right there. All right, then we get to 4 pi over 6, which is 2 pi over 3. So right here is 4 pi over 6. I'm just reducing it, though. Oops. Then we get to 5 pi over 6. That one I can't reduce. Then we get to 6 pi over 6. Well, what's 6 pi over 6? It's just pi. And just keep going. I'm just counting by pi over 6's and reducing when I can. 7 pi over 6. 8 pi over 6 goes here, which reduces to 4 pi over 3. 9 pi over 6, which is 3 pi over 2. 10 pi over 6, which goes here, but we can reduce that, right, and make it 5 pi over 3. So that's where it gets confusing, just because of all the reducing. And then what did we get to? That was 10, and then 11 pi over 6. All right, so we've written all those in, and then we can write the points in. So remember, what were the points? They are root 3 over 2 is what I'm trying to say, and 1/2. Now, this on the other side is the exact same thing. This is going to be negative root 3 over 2 and 1/2. Down here, we're going to have, they're both negative, root 3 over 2 and negative 1/2. So I'm just using symmetry, like a mirror here, right? And oops, positive root 3 over 2 and negative 1/2. So think about it. These are all symmetrical, like this one to this one to this one to this one, right? There's our symmetry. Now, we can also do symmetry this way, right? We can also say, well, this one's the same as this one, just with different coordinates, because look at their distances, right? From the x and y axis are the same. Okay, it's just what quadrant they're in. So these ones, if you remember, were flipped around. So all I'm going to do is take these points and flip them around. This is 1/2 root 3 over 2. Okay, so this is negative 1/2 root 3 over 2. This is down here, negative 1/2 negative root 3 over 2, and 1/2, oops, come on there, come on computer, 1/2 negative root 3 over 2. All right, what we've just done is drawn all the key points on the unit circle. So these are really important points to get used to. Now again, I know with you working at home, and this video has gone really long, that there's a lot here and a lot you're going to skim by it, but this is something you really need to start getting a strong grip on if you're going to continue in math, okay? Getting used to finding these key points, look at the coordinates, how many degrees does it take to get there, how many radians, right? Don't forget, the radian is what does it take to measure around. So if someone says, all right, what's the terminal point at 30 degrees or pi over 6? The pi over 6 is the length measuring around. The 30 degrees is how much we rotated, right? And that would be the terminal point. All right, so we're just going to do a few examples of this, and then we'll be done the longest lesson ever. Okay, so we're going to do 4 examples, and I wanted to do this as a separate lesson, but there'd be no point. So there's no point in trying to cut this bit long lesson short. I might as well just keep it rolling because the next lesson's super short. All right, so examples. For each angular radian measure, we're going to determine the terminal point along with the first positive and first negative coterminal angles. So I'll explain what that means as we start. So we want to start with 45 degrees. So now, finding the terminal point is really easy for this, right? 45 degrees, where is that? We got a unit circle. Boom, it's right there, right? There's 45 degrees. The radian measure is pi over 4. So if it said find the radian measure, we could do that. So that's really easy. There's our answer, right? So again, I've got the unit circle there, but let's say we had like a blank graph on a quiz or something, you know what I mean? So usually in class, you kind of got to learn the unit circle first. So this is a little more challenging when you don't have it right in front of you, right? But the answer is root 2 over 2. Root 2 over 2. There's the terminal point. Now, notice how theta, I put a little 1 next to it. That just means the first angle, the terminal angle, okay? So there it is. Now, we want to find some coterminal angles. Let me just label that to be clear. That's called our terminal angle. That's our starting one, right? All right. Now, let's find some coterminal angles. So I want to find the first positive and the first negative. So let's start with the first positive angle. What does that mean? It means, what if I went around the circle one more time? So like I went 45 degrees to get to there. How could I find another angle? All I got to do is add 360 to that, right? And I'd arrive at the same place. So in other words, to find the first coterminal angle, we're just going to call that angle 2 for now. I'm just using the little subscript 1, 2, 3 just to indicate that they're different angles. It's really simple. All we got to do is take 45 degrees and add 360 to it, right? And there you go. What do you get? 405 degrees. So if we travel 405 degrees, we end up at the same place, right? You go 360, and then you go 45 more, and you end up at the same spot. So that's what we call a coterminal angle, okay? So there's my first coterminal. Let me draw it like this here. There, I'm just going to draw a little diagram. There we go. Now, there's the first positive coterminal angle, right? So we'll call that, let me just write that here. This is our first positive, I'll just put a little circle around it, coterminal angle. All right. Let's find the first negative coterminal angle. So how are we going to do that? Well, let's think about it. We're moving the opposite direction, right? So let's call this angle 3. Well, what are we going to do to basically go from here in the negative direction? So remember, this was at the start of the lesson, maybe you forgot, right? When we're moving in the positive direction, we're going this way. We're moving the negative direction, we're going this way. So let's find the first negative angle we'd arrive at after if we moved in the negative direction. So in other words, how many degrees does it take you to go from here to here? Well, it's really easy to figure out. I mean, you can basically look at it and figure it out, or using basic arithmetic, you just take the angle and all you have to do is subtract 360 from it. So instead of adding, you just subtract it. It's that simple. And we get negative 315 degrees. So this that I drew in orange here, from here to here, is 315 degrees, but in the negative direction, right? Because if this is 45, right? Well, what's 360 minus 45? There you go. So that would be our first negative. Let me write that down. First negative coterminal angle. All right. Oops, forgot the L. All right, and that's really all there is to that. So let's do another one here, right? So there you go. So in other words, what am I trying to say? All we're saying right now is, hey, here are 3 angles that all end at the exact same terminal point, right? The terminal point is this guy right here. So let's maybe make that clear. That's the terminal point, because you guys aren't here to ask questions. That's what happens, right? Usually in class, people ask lots of questions, helps clarify things. So again, how did we find the terminal angle? If I drew a diagram, it would look like this, right? And what did the original angle look like? It was this guy right here, right? So if I'm gonna try and label this, there's angle 1. Here's angle 2 that we went around a couple times. Where can I label them? I don't know, we'll call them there. And here's angle 3, right? There you go. So there's 3 possible angles that all end at the same place. Now, you could do this forever. You could keep adding 360 and keep subtracting 360 and finding more. But I think 3 angles is enough for now. All right, let's do another one. Okay, in this example, I'm given a negative angle, right? So we're moving negative 150 degrees. So there's our first angle. So where would that be? Well, if 90 degrees is here, right, there's 90, well, this must be where negative 90 is if we're moving in the negative direction, right? So it's just switched around. So negative 150, this negative 180 is at the same place 180 is, right? They both are here, right here. There's where 180 and negative 180 are. So it's going to be somewhere over here. I'm not going to get too fancy here. All right, but somewhere over there, right? Negative 150. Now, let's see if we can find some other angles to match up with that, right? So there's let me draw my terminal line in here. There we go. My terminal arm, I mean. There we go. So there's angle 1. So they gave us a negative angle. Well, let's find 2 more angles. Let's find the first positive angle, right? So how are we going to find the first coterminal positive angle, right? Coterminal just meaning it lands at the same place. It's terminal with it, coterminal. Ends at the same place. That's basically what it means. Co meaning like together, terminal meaning ends. All right, so let's go, well, what's negative 150 plus 360? Let's just add 360 to it to find the first positive one, right? So 360 minus 150 is 210. So moving in the positive direction, there's where we'd end up right there. There's angle 2. Now again, looking at my big unit circle here, where's that, right? 210 right there. So there's our terminal point. So the terminal point is at negative root 3 over 2, negative 1/2. Okay? So there we go. That's the terminal point we had to find, because it does say the main thing is to determine the terminal point. Okay, I just found it there. Let's find a third angle. So it wants one more. So we have, basically, this is our terminal angle, our starting one. This is our first positive coterminal. They want us to find the first negative coterminal. So we already have one negative, so we just got to find the next one. It's really simple. All we got to do is just subtract 360 from this. So let's just minus 360. Just basically go a full circle more, and you end up back at the same place, and you end up at negative 510 degrees. So in other words, if you go negative 360, you'll end up here, and then you end up going 150 more, and you end up back there, right? So again, if I were to try to draw this, then it would kind of look like this, around 360 in the negative direction, and then stopping there, okay? And that's what angle 3 would look like. So there we go. We got 3 terminal angles, right? All right, so now let's check out 2 more, and then we're done, but I want to do 2 more where it's radians instead of degrees. Okay, so now they're giving us the radian measure, all right? And they're saying T1, T meaning for the terminal angle, right? Except the terminal, we're measuring radians, so it's the length around the outside. So let's think about this. The first one is 5 pi over 4, right? Well, where's 5 pi over 4? Luckily, you can just look at your unit circle here, right? Let's travel around, pi over 2, pi, boom, there's 5 pi over 4 right there. There's where we end at, right? There's 5 pi over 4, and there's our key point, our terminal point we're looking for. So I'm just going to draw kind of a rough diagram here. There it is right there, and we end up at negative root 2 over 2, negative root 2 over 2. So pretty easy to find when you have the unit circle right in front of you. All right, so there's that first one. Now remember, when we're doing this, this is really measuring around the outside, right? How far did we travel, right? So there's T1, right? That's how far we traveled. Now, how are we going to find the first, the next positive one, right? The first coterminal angle. So what are we going to do? We're going to take that T1, right? Let's call it T2 now, okay? And all we got to do is add a full circle to it. Well, what's a full circle in radians? Instead of 360, it's just 2 pi, right? So let's just add that. So we just got to get a common denominator. So this is over 4, so times 2 by 4. We got 8 over 4. 5 plus 8, that's 13 pi over 4. So there you go. That's how long that string would be. So what would that string look like? If I traveled around the outside, I'll just draw it on the inside here. But if I traveled around the outside, right, there's pi over 2, pi, 3 pi over 2, and then you get back to 2 pi. That's one full circle. And then you go again, farther, farther, boom. So that's how long that string is, right? Wrapping around the circle. If we took that string that we wound around the circle and pulled it out, this is how long it would be. Now again, we could write that as a decimal. Let me just bring my calculator up really quick here and go, okay, what's 13 times pi, right, divided by 4? The length of that string is about 10.2 radians, okay? So approximately 10.2 radians. Now again, we just write it like this because this is nicer, right? Instead of having to round it. So that's why we like to leave it like that. But remember, how far was a radian, right? A radian is our radius. So our radius is 1, right? So it's 10 radiuses. That's basically what it is. 10 of these one length piece of strings plus a little more is what it would take to go around this circle, okay? And end at that point. All right, last thing here, let's find the first negative. Okay, so it's the same thing. Instead of adding 360 or adding a full circle, which is 2 pi, we're going to subtract 360 or subtract 2 pi. So it's the same thing. 5 pi over 4 minus 8 pi over 4, and we end up at negative 3 pi over 4. So what does that mean? It means that piece of string, to get to here, but moving in the negative direction, right, it would only be 3 pi over 4 long. That's how long that string is going around the outside. Okay, so if I was to draw that here, it's basically just from here to here, right? That's where T3 is. And again, we can make that a decimal by just dividing it. What's 3 times pi divided by 4? Okay, 2.3 radiuses, right? 2.3 radians. So approximately negative 2.35, right? That's how long that piece of string is wrapped around the outside, okay? I'm going to do one more, and then that is it. All right, last one. Before I get into this, because, okay, we're moving to negative, right? Negative 11 pi over 6. So that means we're moving in the negative direction. We're going this way, right? That's the negative direction. Now you might, if ever you're stumped and you just want to figure, well, what is that in degrees really quick? One final time, is the last time I'm going to mention this for the rest of the year. How do I convert that one last time? So let's say I want to convert that to degrees. Don't forget, you just times it by 180 over pi, okay? So if you're ever stumped or whatever and you want to convert, because I know it's probably easy for a lot of you to work in degrees for now, they cancel out, right? Pi divided by pi. Let's go, what's 11 times 180 divided by 6? And you get 330 degrees. So this is the same thing as having negative 330 degrees, right? Well, if this is positive 330, then this is where negative 330 would be, right? Because if you're traveling positive 330, you'd go from here. So if I'm going negative 330, I'd end up here, okay? So long story short, it's around here somewhere, right? Right there. In fact, I already know it's going to be right here. So I'll just write the point down, and then we can talk about how we could find it different ways. But that's one way, right? Converting it to degrees when you're first starting out can help you out a lot. Okay, so that's where my first one is. That's where negative 11 pi over 6 is. So one way you can figure it out when we're starting out, oof, nice job drawing that circle. Let's try that one more time, is to convert it to degrees, which I know will help a lot of you out, okay? So there we go. So there is, oh, this says angle, right? This is, they're using theta. This should really say T1. All right, not the end of the world, but there you go. There's T1. That's the distance, right? To travel around the outside, okay? Not an angle, but distance. All right, let's find the two coterminals, not the two, because there's infinite coterminal angles, but let's find one more positive and one more negative, basically, is what we're doing. So let's find one positive one to go with this. Okay, so we're just going to add a full circle, which is 2 pi in radians. Just get a common denominator. Pretty easy, right? So this is 12 over pi, or 12 pi over 6, I mean, and you end up with 1 pi over 6. So look, remember how I said it landed right here? Yeah, there it is, right there, right? There's pi over 6. So if we went in the positive direction, it would be there. So pi over 6, right? That's where T2 would be. So I could have found it that way, right? Just by finding the positive. So the reason I'm doing this with you too is this is a way to find other spots or other ways to find the same spot on the unit circle, right? So I can travel negative 11 pi over 6, or I could just travel pi over 6 in the positive direction. Either way, I end at the same terminal point, right? That's the key. We end right here no matter what, which is at 30 degrees, right? All right, and let's find one more negative. We got one negative, we got one positive. Let's find one more negative. Again, it's really easy. All we got to do is subtract 2 pi from that. All right, so to do that, we need a common denominator of 6. So we got negative, 12 over 6. Sorry, I know you're bored of this video. I think I'm losing my mind too. So what do we got here? Negative 23 pi over 6, right? And that would be like if we traveled all the way around the circle once, all the way around almost again, all the way to here, right? That's what that is. That's how long that string is, right? So if we were to draw that, I'll just draw it here. The idea is like we've gone around 2 pi, which is a full circle in the negative direction, and then we went around 11 pi over 6, and boom, we hit there. And that's how long that string is. And again, you could convert that to degrees to figure out the degree by timesing it by 180 over pi, or we can make it a decimal by dividing. I'm just curious. I want to see what that is. 23 times pi divided by 6, and it is 12.04. So approximately 12, right? That's about 12 radians, right? So our radius is 1, so it would take 12 of this length, right? This radius length here. If we took that string and we bent it, remember that's the whole idea. That's what a radian is. It's one of our radius. If we take that radius and we bent it so it goes around our circle, it would take a little more than 12, right? Like 1, 2, 3, 4, 5, 6, 7, you know, to go around and get there, okay? All right, long lesson. If you made it through, that's amazing. If you didn't, I can't totally blame you. But this is stuff that you got to start getting a good grip on if you're going to move into grade 12 and if you're going to university in a field that really requires a lot of math, okay? So if that might be you, it's definitely some stuff you want to review and study, and not just once to get through the homework. That's the hard thing to impress upon you. I get it. I know when I was your age, it was the same thing. It's not about just doing the homework to get it done to get the mark. That's all baloney in the end. Like as you get older, those of you that do well will start realizing that's all hogwash. That doesn't matter. to get the homework done, to do this. Like, that should just be done as part of the learning, right? If you really care and it's important to you, you'll end up getting good grades. You'll get every piece of homework done because that's what it takes to learn. No offense to the rest of you, because I was like this when I was your age. If you don't care about it and it doesn't interest you, it's hard to really get you to learn this stuff, because it takes a personal drive and personal interest and real personal dedication, right? It's not grade school where we can just kind of like put you through drills and make you learn some skills. We're getting to the level of math now where the concepts are getting bigger, and it takes you time to not just like a day of watching a video, but day after day watching videos, doing work, practicing questions, your own personal interest and drive. And like I said, I don't blame you if you're not at that point, but some of you might not be at that point, and you will be someday. And I'm not saying you'll look back with regret, but one day you'll have to come back and really study this stuff because you'll have a goal. You'll want to learn it, okay? And maybe not. Maybe it's in something else completely different from math, and that's pretty cool too. So thanks for hanging in there, guys.